This is Dr. D. Govardhan, Professor and Dean, Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad. Here today we are discussing the concepts of LMTD and NTU methods in heat and mass transfer subject. A logarithmic mean temperature difference. This is known as LMTD now. In heat exchangers, the thermal potential the responsible for the heat exchange between the hot and cold fluids. Here when we are taking now, drawing a figure now, graph, this is between this length, that is the length of the flow or the length of the pipe to the temperature now. Here we are taking the two pipes here which are concentric, in which both the fluids are flowing in the same directions now. The heat energy is now transferring from the fluid which is having higher temperature to the fluid which is having lower in temperature. So in this case, capital T HI is representing this inlet temperature of the hot fluid, and TCI is representing the temperature of cold fluid at inlet. Here both are now moving parallel to each other. That is, heat energy is extracted from the fluid from the fluid which is having higher temperature. Gradually, when they are going just out almost, they are now having nearer to the same temperature now. But earlier nothing but it is having higher values, but at the outlet it is nothing but theta values now. That is, the temperature of the hot fluid is gradually decreases while leaving the tube now. At the same time, the temperature of the cold fluid gradually increases and it is becoming TCO, O is nothing but representing a outlet now. This is in the case of parallel flow heat exchanger now. In parallel flow heat exchanger, the thermal potential is parallel heat exchanger is maximum at the inlet and decreases the length and a minimum at the exit as shown in a figure now. In counterflow directions, counterflow heat exchanger now, the two fluids are moving in opposite directions now. Here now, in this case, if I take the temperature now, it is there. The temperature THI is representing the temperature of the hot fluid at the inlet, and it is moving, assume, just from left to toward the right side now. By leaving, it is having temperature THO now, separating now. But here now, at the same position now, when the hot fluid is leaving now, the cold fluid is entering into the tube. Since the temperature difference is very, very less now, while moving toward the here now, cold fluid is moving from right to left position now. Since the temperature of the hot fluid is comparatively very high, hence the heat energy flows continuously from higher temperature to lower temperature. When it is leaving, that is at this position now, it is having again temperature TCO now. If we observe this entire its flow length, the temperature difference between the hot fluid as well as the cold fluid almost remains the same now. But in the case of condensers, evaporators now, I am taking the example here, the condenser now. Here, the heat energy is now extracting from the fluid which is having higher temperature to a body lower temperature. When the lower temperature fluid remains constant, only it changes its phase. That is the latent heat it changes now. So particularly this happened in condensers now. But in the case of again evaporator, the temperature of the hot fluid remains constant. That is example is steam now. Here, when assume just both are moving in the same direction, so that is the parallel flow. The fluid which is having lower temperature extract the heat energy from the steam now. That means which is maintaining at constant temperature, continues to extract while leaving almost it reaches nearer to the temperature of the hot fluid. But in this case, the temperature of the hot fluid remains constant because when you take the steam, the 100 degrees centigrade remains same, but the latent heat of that steam is extracted by this cold fluid to raise its temperature now. So this is nothing but happen in evaporator now. So in this exchanges, condenser and evaporation, the change in thermal potential along the length occurs only on account of change in temperature of the fluids, while the temperature of other fluids always remains the constant. So the figure here now 11 and 12 is representing the temperature changes when the two fluids are moving in the same direction. So in this case, the temperature of in the case of condenser, the temperature of the whole body remains constant, but in the case of evaporator, the temperature of the hot fluids remains constant, but heat energy flows from one fluid to another fluid by using its latent heat now. The heat transfer rate in heat exchanger at a particular length is calculated by using the relationship Q is equal to UA TH minus TC now. We use representing now this overall heat transfer coefficient. A is the area of the cross section, TH is representing the temperature of the hot fluid, TC is representing temperature of the cold fluid now. So this equation it can be represented as now, but if we observe the previous figures, the temperature of the hot fluid as well as the temperature of the cold fluid is not the same entire its length. That is, the temperature of the hot fluid is decreases. At the same time, the temperature of the hot fluid is cold fluid is gradually increases now. So here TH minus TC is not the same for the entire its length. Hence, this difference TH minus TC, this is called difference is delta T. We have to take it as minimum values, mean values now. So therefore, the overall heat transfer in case of heat exchanger can be expressed as Q is equal to U into A into delta Tm, where delta T is representing the temperature difference between the hot fluid to the cold fluid by taking a mean of entire its length now. So where U is representing the overall heat transfer coefficient, generally it is expressed in watts per meter square per degree Kelvin. A is the area of the cross section, generally it is expressed in MKS units meter square, and delta Tm is representing the temperature difference, or is also called logarithm temperature difference. It is expressed in degree Kelvin. Okay, for the wall when we are taking now, the overall heat transfer coefficient can be determined as follows. As in here now, hot fluid is one side of the wall is there, which is having temperature is equal to T0. Here wall temperature is there. Here assume this is represented TS1 it is there, and other side TS2, and fluid temperature other side of the wall having this cold fluid having temperature is equal to TC now. So in this mechanisms now, from the hot fluid, the heat energy is flowing to the inner surface of the wall by using the convection process. So here the first one is that nothing but from the temperature TH, that is the temperature of the hot fluid is there, from this fluid to the wall which is maintaining at TS here 1 now. Here the heat energy is flowing from the fluid to the hot surface by using convection process. Here from the inner surface of the wall to the outer surfaces, the heat energy is flowing here now by using convection process. After that again, from the outer surface of the wall to the cold fluid, the heat energy is flowing by using convection process now. So here we are assuming the consider the wall thickness is equal to delta. This thickness is equal to delta. Thermal conductivity of the material is equal to here the K. The temperature of inner wall surfaces is given. Inner wall means here meaning is the temperature of the wall which is having in contact with the hot fluid is given as TS1. The temperature of the outside wall, that is which is having in contact with the cold fluid, it is represented as the TS2. The convective heat transfer coefficient between hot fluid to the inner surface is represented as HI, and between air cold fluid to the outer surface is equal to air H naught now. So heat transfer to the wall surface by hot fluid is expressed as now Q is equal to hot surface to the wall is given by HI into A TH minus TS1. It is by using convection process, where HI is representing air coefficient of convection of heat transfer air from the hot fluid to the inner surface of the wall. From this relation we got to Q divided by HIA is equal to TH minus TS1. Assume this is the equation number 1. Similarly, the amount of heat energy that is flowing through the wall, because you are taking the figure like this, air from the wall which is having temperature TS1 to outside temperature TS2. Here this process is called conduction process. It is given by the equations now, that is Q is equal to K into A into T1, that means TS1 minus TS2 divided by the length is equal to delta now. So this is the represented here in these equations. It can be modified as here equal to Q into delta divided by K into A is equal to TS1 minus TS2. This is the equation number 2 now. Similarly, heat convected to the cold fluid by the wall surface is expressed as now, that is Q is equal to H naught into A TS1 minus here TSI minus TC. From this relationship we got to TS2 minus TC. From this relation we got to Q by H naught A is equal to TS2 minus TC now, where TS2 is representing the temperature of the outer wall, but here it is having connected with the fluid now. Assume TC is representing the temperature of the cold fluid now. From this relationship we got to, that is adding this equation 1, 2 and 3 equations now, we got to Q is equal to 1 by HIA plus delta divided by K into A, 1 by H naught A is equal to TH minus TF now. So from this relation we got to Q is equal to TH minus TC divided by 1 by HIA plus delta divided by K, 1 by H naught A. This entire quantity is the represented as only, that is nothing but 1 by U now, where U, 1 by U is representing the overall thermal resistance offered by the system, that nothing but from the hot fluid to the surface and the surface to the cold fluid. It is called overall thermal resistance, which is represented as 1 by U, and the reciprocal value of 1 by U is equal to U, which is called overall thermal heat transfer coefficient now. Hence, it can be written as now Q is equal to U into A TH minus TC now. So comparing these two equations now, that is 4 and 5 we got. 4 and 5 we got now. UA into TH minus TC divided by TH minus TC divided by 1 by HIA plus delta K into A plus 1 by H naught A. This we got it now, because here heat energy is constant now. From this relation, so 1 by UA is equal to 1 by HIA plus delta Ka plus 1 by H naught A now. So here now the surface area, if it is a constant now, but its values just change up from inner to outer surfaces little. But when it is a change in values, when it is neglected in the case of tubes now, but in the case of slab, that is it is having the same area. Hence, when you are taking A is the common factor on both sides, the value it can be represented as 1 by U is equal to 1 by HI plus delta by K plus 1 by H naught. This is representing the equation for the overall heat transfer coefficient for the plane wall, which is useful in determining the net quantity of heat energy flows from hot to fluid to the cold fluid, particularly in heat exchanger process. So the performance of the heat exchangers can be analyzed by using two methods now. Here one is logarithmic mean temperature difference. Simply it is called LMTD method. The second one is effectiveness of number of transfer unit, that is called the NTU method. Okay, first one I am taking logarithmic mean temperature difference LMTD now. The LMTD method is used when the temperature of both the fluids, that is at inlet and the outlet of the heat exchangers, are known now. That is, if I take this example in previous one only, here it is there, assume this is the wall thickness of the tubes now. Here T0 as well as the TC, here it is given now, H, assume H is representing temperature of the fluid which is higher temperature, TC is representing temperature of the fluid which is cold temperature. If you know these two, then only logarithmic mean temperature method is used for analyzing the performance of the heat exchangers now. The performance analysis by method is carried out by making certain assumptions now. The overall heat transfer coefficient to U remains constant along the length of the heat exchangers. That is U is the constant. Overall heat transfer coefficient is the constant. The second one is the specific heats and mass flow rates of both the fluids remains constant. And the third one, the heat exchanger is perfectly insulated and no loss of heat occurs. The axial conditions along the pipes is negligible now. Okay, these are the four assumptions we made for the analyzing the performance of the heat exchangers by using LMTD process now. Here parallel flow heat exchangers now. In parallel flow heat exchangers, in this case, both the fluids are flowing in the same direction, so as shown in figure. Let the temperature at the inlet of the cold fluid is represented here now, TC, I, and TH is representing the temperature of the hot fluid at inlet temperature. The difference of these two temperatures, assume it is represented as T, theta, I now. When the fluid is flowing now, both are moving in the same direction. So, according to this problem, so the fluid is flowing from left hand side toward the right hand side. The temperature of the hot fluid is gradually decreases to TH naught now. That is O is nothing but representing at outside. Similarly, for the cold fluid also, the temperature increases to TC at the outlet, that is written as TSO. This temperature difference is very less when comparing with the difference of TH and TC. That is, the temperature of the hot fluid is decreasing, the temperature of cold fluid is increasing, and the temperature difference at the outlet of the tube here very less. It is represented as TO now. O is nothing but the temperature difference at the outlet. Ti is representing the temperature difference at the inlet now. Let MH and MC are the mass flow rates of hot and cold fluids. THI and THO are the temperature of the hot fluid at the inlet as well as the outlet of the heat exchanger. TSI, TCI, that is the temperature of the cold fluid at inlet. TCO, the temperature of the cold fluid at outlet, or the temperature of the cold fluid at inlet and outlet of the exchangers. And CPH and CPC, here the certificate at constant pressure of hot fluid, that the cold fluids are represented CPH and CPC. TI is representing the temperature difference between the hot fluid and cold fluid at the inlet of the heat exchangers. Similarly, theta naught is representing the temperature difference between the inlet and that is temperature difference between hot and cold fluids at the outlet now. So TA and T0 completed. Hence TA is equal to the THI minus TCI and T0 is equal to, we can take the difference of hot fluid at the outlet to the cold fluid at the outlet is represented in equation number 8 now. CH and CEC are heat capacity rates of hot and cold fluids respectively. So according to the equation we can write heat capacity is equal to, generally it can be represented as here Q is equal to M CP T2 minus here now T1 minus T2 and so on. Now here heat capacity is equal to, it is equal to MH into CPH for that fluid. Similarly for the cold it is equal to MC into C into PC now. So determination of mean temperature difference. In a single disk tube parallel flow heat exchanger as shown in figure 3 now, this figure it is given. The hot fluid is at THI, that THI is representing the temperature of the hot fluids at the inlet and leaves at THO here at this position. But while at the inlet it is having higher temperature, while fluid is flowing according to this figure from left to right, the temperature of the hot fluid decreases along the length of the pipe, while leaving at the outlet it is equal to TH I is represented now. Similarly for the cold fluid now, the flow rates at the specific rates are MC CC and MH CH respectively now. The product of MC is also known as heat capacity. Sometimes it is denoted by CH and CC now. Here the temperature, that is here now, the average when you are the difference of or the mean of here, the mean of the temperatures of hot fluid and cold fluid, it is gradually increases now here when we are moving from left to right positions like this. Now here we are taking now delta Q is equal to, that is the amount of heat energy that is extracted from hot fluid is equal to MHCH into DTH, which is the amount of heat energy that is extracted from the hot fluid that is utilized to raise the temperature of the cold fluid. That is according to the system, this is can be written as MC CC D TC now. That is the change in temperature of the cold fluid now. It is represented in equation number 5. The total E flow is equal to, here Q is equal to MHCH. Here DTH is nothing but equal to the representing now THA, that is temperature at the inlet to the temperature of the outlet, should be equal to MCCC, T temperature of the cold body, that is cold fluid at outlet to the temperature at the inlet now, because here the temperature increases now. Just using these equations we got to DTH is equal to minus of DQ into divided by MHCH, or DTC is equal to DQ divided by MCCC from the equation number 6 now. Okay, DTH minus DTC is equal to, we can represent it as D of TH minus TC, and combining this equation it is equal to DQ into 1 by MHCH plus 1 by MCCC, the equation number 7 now. From this equation we got to dq is equal to u into dA into th minus tc. Is already equation is given for determination of amount of heat energy that flowing, where u is representing the overall heat transfer coefficient to dA is equal to surface area, th minus tc is representing the temperature difference between the two fluids now. Thus, from these two equations we are having, dividing this one equation by another equation, we got d into th minus dc from this value divided by th minus tc, it is equal to, here now uda into, we are having 1 by mhch plus 1 by mccc now. So, integrating from the inlet to the outlet to the pipe, that is, we can take the temperature is nothing but from inlet to outlet, that is th minus tc, it should be equal to minus of ua into 1 by MHCH plus 1 by MCCC. So substitute the values in these equations we got finally. MHCH is equal to Q divided by T HI minus T H naught, and MCC is equal to, we can write from this equation we got Q divided by T CO, that is the temperature of the cold fluid at outlet, minus TCA representing the temperature of the cold fluid at the inlet now. So from this relation we got that log of delta T naught divided by delta Ti is equal to UA divided by Q into THI minus T naught plus TCO minus TCA now. Or the same equation it can be written as the log of delta T naught divided by delta Ti is equal to minus of UA, U is equal to overall heat transfer coefficient, A is equal to area divided by amount of heat energy, that is exerted Q. It is equal to the sum of THI minus THO plus TCO minus TCA now. Or it can be written as UA divided by Q now, THO minus TCI, that is representing the here the temperature difference at the inlet of the exchanger, minus of THI minus TCI, that is the temperature at the inlet of hot fluid to the inlet of the cold fluids. So these values are already, we determined this values is equal to UA into, it can be written as delta of T naught minus delta of T I, that is the temperature of the hot fluid to the here. It can be written as now delta T naught minus delta Ti divided by log of here given delta T naught divided by delta Ti now, where delta T and delta I are the difference in temperature between the hot and cold fluids at the inlet and outlet respectively now. So comparing these equations now, the mean temperature is given by delta T mean is equal to, because we have taken Q is equal to UA into DT in nothing but we have taken mean now. So comparing this equation we got delta T mean is equal to delta T naught minus delta Ti divided by log of delta T naught divided by delta T1 now. The temperature difference, this is called here now mean temperature difference. Simply it is called LMTD, that is logarithmic mean temperature difference. Here it is represented. Hence the total energy which is flowing, it can be from hot fluid to cold fluid, is given by UA into LMTD, where LMTD is representing the mean temperature difference. The equal capacity of both the fluids are there now. That is MHCH is equal to MCCC. The temperature variation is shown in figure here is given 12.7, it is given now, that is A and B for parallel as well as the counterflow arrangements. In a parallel flow heat exchanger now, parallel flow heat exchanger, the temperature will be equal for both the sides, that is delta TH is equal to delta TC. The slope of the lines will be equal but in opposite directions. Here now, the temperature difference between at the outlet is equal to, both are equal, but both are almost parallel to each other. The slope of this lines remains constant. But in the case of parallel flow of fluids now, the temperature difference at the inlet is maximum and this values decreases when the fluids are leaving, that is at the outlet now. In the case of counterflow, the temperature difference is same at all locations. That is the temperature difference is here the constant now, and LMTD will be of 0 by 0 form, and LMTD is equal to here THI minus TCO. It is almost constant for along the length of the pipe now. In the case of two passes, that is nothing but here one side, two sides will be the cross flow as well as the other arrangements, the LMTD obtained by using single tube arrangement does not provide the correct average temperature, and the correction factor has to be implemented now. The two parameters are generally found to influence the value of correction factor. The one is called capacity ratio and the second one is called the effectiveness. These are represented as R and P now, where capacity ratio is equal to the hot fluid temperature change divided by cold fluid temperature change, which is equal to THI minus THO divided by TCO minus TCA. The effectiveness P is equal to the minimum heat capacity of fluid temperature raised to the difference between the inlet temperature. That is here T2 minus T1 divided by here T minus T1. These ratios is called here. Now one is the capacity ratio, one more the effectiveness P. Generally it is applicable when it is having two passes. Okay, I collected this entire material from the textbooks as well as the reference books which are mentioned here now. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.